And remember that you predominantly can interact through the Q&A. So write those questions in as Jamie's going along with his presentation or when I start presenting. But you can, if you'd like, raise your hand. And we do have the functionality to unmute you if you want to discuss something in a bit more detail. We do have a fair bit to cover today as well. And tomorrow's session, we do have a little bit more time for some general open discussion if people want to go down different paths. So today is about starting to delve into the design decisions to be made, how you make design decisions about barriers, which barrier you use, offsets, lengths of barriers, and a whole raft of different design specifics. So we've got Jamie back. Jamie's spent many, many years designing barriers in using different methodologies throughout his career. So he'll be able to share some examples of past practice and more contemporary practices. So keep those questions coming in the Q&A, and I think I will hand it over to you, Jamie. I'll be back right at the end to just wrap things up with a little bit of motorcycle safety thinking around road safety barriers and what we can do in that space. But over to you, Jamie. We can see your slides. Looks good, and remember your cursor's somewhere. Yes, there. That's it. Yeah, that's the one. All right. Keep the questions coming in, everybody, as Jamie goes, and I'll be popping back in and out as we tick along.
Thanks, Ken, and morning, everyone. So I'd like to take you through a bit of an intro to barrier design. It can be a long and involved process, and some of the guidance that's available sets out some long-winded processes for barrier design. Each designer has their own way of doing things, and I really just want to point out some of the key considerations that you should be thinking about if you're involved in designing or installing or maintaining a barrier. So the relevant guidance again is primarily Austroad's Guide to Road Design Part 6, which is, as I mentioned the other day, has recently been updated. The sections around barrier design have not. So if you're familiar with that guide, nothing has really changed in that regard. There has been significant change around when to install a barrier and the assessment of roadsides in terms of risk, but the barrier design process has not. There is a flowchart in the guide which spells out a long-winded process of, I think, 16 steps. I never once have used that process from step 1 to 16, and I wouldn't expect anyone else to, but it really does capture all the things that you need to think about. With experience, you sort of learn some hacks and shortcuts through that process. And today I'd really like to pull out some of the more important parts from that process. There is a brief RMS supplement to the guide. It hasn't been updated after the Austroad's guide was updated last year. So stay tuned for an update to that shortly, I would expect. RMS also produces some standard drawings around things like public domain, barrier systems, connections to bridges, and so on. The suppliers these days put out some really good information around their products. It wasn't always the case early days, but these days their information is really thorough. There's sometimes some videos as well, and a suite of drawings that accompany each product. It's sometimes the case that you might like to refer to that information, which is available at their websites. Some of the key parts, the key aspects of each barrier system are contained within the TCU documents that Evan would have spoken to you about yesterday, and you can find at the RMS website, but there is more to it, and you can find some of that information in the supplier's manuals at their website, or pick up the phone and talk to your supplier. The website, as I mentioned, contains all of those TCUs. It also has I think a really useful frequently asked questions section, which captures a lot of the provides some responses to some of the common questions around barrier design and selection. So the first step when we're thinking about choosing Selecting a barrier type and designing one is to think about where it's located and what its function is. So there's a few distinct cases there. Is our barrier at the roadside, where its primary function is to stop an errant vehicle from leaving the road and potentially hitting a tree or rolling over? Is it in a median, where we're primarily concerned about cross carriageway crashes, head-ons? At bridges, we typically beef things up in terms of containment level because we're concerned about that secondary event where the vehicle leaves the bridge and ends up on the roadway or the railway line or in the stream below. At work sites, we're typically dealing with lower speeds, and our primary concern is the workers located behind those barriers. So we have a different suite of products that we use in temporary situations. On the roadside, we might use a guard fence product, as you can see there, and I will note that many of the pictures that you see here are now superseded products. There is a fairly new suite of guard fence terminals and of wire rope products that are on the market now and that are accepted for use, and many of these older products have become legacy in recent months. Another guard fence at the roadside. So here we really are concerned about that possibility of an errant vehicle entering the roadside and striking a tree, rolling over. In this case, we have a structure at the bottom of the hill. So there's that possibility of the vehicle striking an object or crossing onto that non-traversable batter. Roadside barriers are typically it's flexible. We choose as flexible a system as we can provide subject to the site constraints, as opposed to bridge barriers, for instance, where we really beef up the containment level and generally prefer a concrete barrier. Here we have a windy road, popular with motorcycles, and you can see a motorcycle rub rail at the base, and Ken will talk more about these sort of treatments shortly. Wire rope barriers are a popular treatment at the roadside as well. And there are a few examples. In the median, we need to be mindful of some different considerations, such as how much does the barrier deflect. Wire rope is a popular choice, although it does deflect by more than our guard fence products typically. We might have a back-to-back guard fence product in the median. In an urban or high-speed, high-volume environment such as this, concrete is typically the go-to because we have a high proportion or a high number of heavy vehicles, and we must prevent those vehicles from penetrating the barrier and ending up on the wrong side of the road. We might also have some critical infrastructure, such as the gantries that you can see there that need protecting. Given the volumes and the importance of these routes, if a less rigid system was provided, it would likely be impacted regularly. The maintenance burden that would create is also a consideration. At a bridge, we might go with a barrier as you see here. It's a tri-beam installation, so it's a higher containment level than our typical roadside barriers. We might step that up to a steel rail system. Oops. But more commonly, we actually see concrete or perhaps concrete with a steel extension, especially on major roads where we have bridges. Now, Evan took you through the different products that are available and the testing regimes that they're put through. We categorise longitudinal barriers into those three categories that you've heard about: rigid or bridge barriers, semi-rigid systems, or flexible. Each of those longitudinal systems requires an end treatment. It will be an end terminal in the case of a flexible product or a semi-rigid product. If it's a rigid barrier, we might want to shield the exposed end of that with a crash cushion, sometimes referred to as an impact attenuator, or transition rigid barrier to a more flexible system and then terminate. We sometimes use a point protector where we don't have the length available to install a longitudinal system perhaps. There are a couple of point protection systems available, which are generally treated as a last resort where we can't do something better.
So Jamie, just what's an example of a point protector?
Point protector is the Raptor crash cushion is the prime example. So it's a plastic system that we sometimes install around utility poles. In theory, it provides 360-degree protection. It should be used in relatively low speed environments. It's a good product where we've got poles located near roundabouts, for instance, where vehicles might be departing the road at all sorts of different angles. It does swivel about the pole that it's installed around. So they do have their place. Sometimes they're used inappropriately. Sometimes they're used as a last resort in high-speed environments, say, where we just can't do anything. So, yeah.
So, yeah, and in New South Wales, they're used up to 50 kilometres or accepted for use up to 50 kilometres per hour. In Victoria, we use them up to 80 kilometres per hour. So I wonder there might be some leniency if you had some very tricky scenarios to do a sort of exemption report to use one of those. But yeah, as Jamie said, the last resort really. Another question that's come in, the difference between a crash cushion and an impact attenuator. Well, it's just the name, isn't it?
Yeah, no, there isn't a difference. They're different terms for the same thing. So that's probably incorrect. I should just delete one or the other.
But yeah, no, fair enough, because some people use some terms and some use others, and so you don't want to miss out there. Good question though, thank you. Keep the questions coming in.
So any given barrier scenario will either be a permanent or a temporary one, and there are different suites of products available for each of those situations. So it's important as a designer to be aware of the ins and outs of the available systems. The rigid barrier category, we see them typically at bridges, perhaps that median of an urban freeway. We see them in those situations because of that potential for a secondary event if and when a vehicle does penetrate the barrier. So they're located where we must prevent that heavy vehicle in particular from penetrating the barrier at all costs. So at bridges where there might be a roadway below that we are concerned about, of course, as well as the impact on the occupant of that vehicle as it drops over the edge. There's barriers on either side of a divided urban freeway. The benefits of rigid barriers are that when they're struck, they sustain very little damage, if any. So from a maintenance point of view, that's certainly an advantage. Because of that, though, they're the least forgiving system on the occupants of errant vehicles. So we shouldn't be installing them in locations where there's potential for high impact angles, particularly at high speeds. On a fairly constrained environment, such as the urban freeway you can see there, with its generous geometry, there's not a huge opportunity for someone to develop a high impact angle at high speed. So we do rarely see serious crashes into these barriers in this sort of situation. Low maintenance, they perform again and again without any intervention. Typically, they have a higher containment level than more flexible systems. But the downside, as I say, is the impact severity. So because of that, we need to be mindful of where and when we install rigid barriers. In the semi-rigid category, we have our guard fence products, and on the left you can see G4 system, now legacy. On the right, we have a Thri-beam system, both falling into the semi-rigid category. There is a hell of a lot of old style G4, Type B and the like guard fence on the network. It has been the favourite of years past. These systems deflect by a little bit, certainly more than a rigid system. We're talking somewhere in the order of 1 metre. Because of that deflection, they're more forgiving on the occupants of the errant vehicle than a more rigid system. Typically, the damage upon impact is fairly localised, so the barrier can sustain subsequent impacts and perform well. So it doesn't need that immediate maintenance intervention in the most part. Sometimes with some serious impacts, it does. Semi-rigid systems can be transitioned directly to rigid barriers, which is typically done on approaches to structures, for instance. They don't have the same limitations on them as wire rope in terms of being located on roadways with tight geometry, so short radius curves, crests and sags, and so on. In the flexible barrier category, we have 2 types of systems. On the left, we have wire rope, and on the right, we have the flexible W-beam system or category. So there are a few alternatives in each camp. Again, the picture there on the left is a now legacy wire rope product. There is a new suite of MASH tested wire ropes on the market, which look on the whole quite a bit different to the older products. They've been beefed up, their height has increased, their foundation details have changed. Wire rope products do deflect by more than flexible W-beam products, and because of that, they provide a slightly better safety outcome. There's not a lot in it though, and they're both generally grouped together in this flexible category, and you may choose one or the other and achieve a similar safety outcome.
I mean, just a question that was back on rigid barrier systems. What is the deflection assumed in the design of a rigid barrier? Is it nothing?
Yeah, 0. Look, they will deflect by a very small amount. It depends on their, if they're on a structure and they're an integrated part of the structure, their deflection is going to be negligible or 0. If they're not anchored, there'll be some deflection. We sometimes see rigid concrete barriers used in temporary situations. So in those cases, there'll be a small amount of deflection, but I would assume 0. But if it's not anchored, you ought to assume that it will move by some degree.
But you would still allow a working width, a roll allowance, or you're going to get to roll allowances, aren't you, of heavy vehicles?
Yeah, you ought to. You're right. Yep. So yeah, we'll talk a little bit about that in a little while. So on the left, wire rope, on the right, flexible W-beam. They both deflect by a fair bit. So they really do have provide a cushioning effect to the occupants of the errant vehicles. They're really quite forgiving, great crash reduction factors. But in the case of wire rope in particular, a single impact can render the whole length of the barrier ineffective. So they do need to be attended to fairly quickly to ensure that the roadside remains protected. Flexible W-beam products, that's not such an issue. Certainly it can be if there's a high energy impact, but typically we see some low impact angle glancing type impacts, which will see a small amount of damage to the barrier, and they won't need any attention. Again, the bottom point relates primarily to wire rope products, which have some limitations around how tightly they can be curved, both horizontally and vertically. I mentioned this the other day, but just a little bit of safety barrier philosophy. And really the thinking has changed around this. A quote in the Austroads Guide talks about installing barriers only when it reduces the risk associated with the roadside. We do know that with the newer and particularly the flexible products that it will be the case that the barrier has reduced the risk associated with the roadside. There are a few design things that we need to keep in mind to ensure that we're not introducing potential risks associated with the barrier, but on the whole, introducing a longitudinal barrier, and particularly a flexible one, is a good thing. AASHTO talks about whole of life cost, and this is an increasingly a consideration where we're installing long lengths of continuous barrier. And the comparison is usually made between wire rope and flexible W-beam products. And some research that's been done in Victoria has tried to quantify the whole of life cost of those two systems as part of a mass rollout program. And while flexible W-beam products generally have a greater initial cost, over the whole of the life of the treatment, they have a significantly lower whole of life cost. And that's primarily due to their reduced maintenance requirements. Our preference, though, should be for the most flexible system. So wire rope being at the top of the list from a safety point of view. So wire rope, then flexible W-beam, semi-rigid and rigid, subject to other constraints at the site and other things that might be happening at the roadside. Obviously at structures where there's a piece of critical infrastructure, we need to beef things up and we might consider a rigid system. When thinking about whether to install a barrier or not and our choice of system, you really need to keep in mind the speeds at that location. If our speeds are sufficiently low, perhaps 60 or less, an impact with a roadside object is unlikely to lead to a fatal or serious injury, and we typically wouldn't install barriers. It's more in the high-speed environments that we choose to do so. If there is a secondary risk, so regardless of speeds, at a cliff or a vertical drop at a structure, we would choose to install a barrier because of that secondary possibility. And really do know the ins and outs of the different systems available. So it's important to have a good concept of the differences between our semi-rigid, rigid and flexible products. And within each of those categories, understand that there is some variation in the way that those different accepted products perform, geometrically, how they look, their heights, minimum lengths, post spacings, foundation depths, all these types of things. Right, so now I'd like to get into a few of the key design steps. The first thing that we must do is to get out on site and understand our hazard, locate it in relation to the road. So how close is the hazard to the edge of the road? And what is the furthest point of the hazard from the road? Because really that's the width that we're looking to shield motorists from. And we use this term protected width to describe that width of roadside that we're looking to prevent an errant vehicle from entering. Once we've identified where the hazard is, we can think about how long a barrier would need to be to effectively shield it. Hand in hand is where that barrier is located in relation to the road. The closer a barrier is to the object or the hazard, the shorter it needs to be to effectively shield it. So we need to locate the barrier in relation to the traffic lane, the edge of the road. There may be a shoulder, perhaps it's got a sealed portion and an unsealed portion. There might then be an unsealed verge. If there's curb in play, that might influence our lateral offset of our barrier. Our slopes adjacent to the road might have a bearing on where our barrier sits. providing run-out areas. So that's a relatively flat, clear area near the start of a barrier that we like to provide, and I'll go into that in a little bit more detail shortly. Providing a run-out area might influence where our barrier starts and ends. Transitioning to other barrier systems is something that we need to be keep in mind as well. If there are existing barriers on site, we might look to connect them directly, to overlap them. There might be a structure that requires a higher containment level that we need to deal with. I will go through some of these considerations in a bit more detail shortly. This is really just a bit of a summary slide. Barrier selection, choose the most flexible product that you can, subject to the limitations or the constraints at the site. And then we need to choose appropriate terminals and transitions. So this certainly isn't set out in a set order. It really is quite an iterative process. And some of that comes with experience. You understand, or you come to understand that on particularly constrained sites, we don't have the luxury of providing a wire rope safety barrier, for instance. We might need to compromise on our desired offset relative to the edge of the road. So there's a lot of back and forth, and there's a lot of compromise often in retrofit situations, especially on some of the desirable things that we'd like to achieve. So I mentioned retrofit, and there are two distinct cases when it comes to barrier design. One is the retrofit of the barrier to an existing road. Perhaps we've identified a high crash risk. Perhaps you've gone through the process in the Austroads guide and compared your risk scores against the NRRT, and you've identified that a certain section of road should be shielded with barriers. And you've chosen to go about installing barriers at isolated hazards, the highest risk hazards along that road. You likely do not have a survey for that road. You might have an aerial photo, as you can see here. So a design might be presented on that aerial photo base, and it could look something like this. I won't go into the detail. Don't concern yourselves with the notation here. This is a shorthand notation that VicRoads sometimes uses to describe barrier installations. And it's intended to provide all the information that's required by an installer to set out the designed barrier about a particular hazard. So it really is important to nominate some points that can be found out on site that barrier can be located about. So you can see here a reference point, which is a tree. And a lot of the values in this little table here relate to setting that barrier out about that tree. So this information provides the barrier's offset in relation to the road, its length either side of that tree, and so on. It nominates the type of product, terminals, and all that required information. The other case is a new roadworks project or a significant road upgrade where there's other design work happening. You have survey information, you have other design information that can be utilised as part of the barrier design process. And the barriers that have been designed will typically appear on an alignment plan or some other roadworks drawing. They might appear on a standalone barrier design plan or a roadside furniture plan or something like that, but typically they'll appear on an alignment plan like this. The amount of information that's provided to describe that barrier is pretty minimal, really. We identify some start and end points of the barrier. In fact, they're not quite the start and end points, they're the points of need, and I'll talk about this a bit more shortly. We've got some chainages. We have a chainage line. We don't nominate the barriers offset from the edge line, although you can quite easily scale that off or interrogate the drawings electronically and measure some of these things. So really quite minimal information provided there, and we're perhaps often working off some survey information as much as we're getting out rather than getting out on site and taking all sorts of measurements as we need to do in a retrofit. Another example of a barrier retrofit, in this case, it's a continuous barrier design job. So really the art in a continuous barrier design is about how and where we create breaks in the barriers for maintenance access, emergency vehicles, and so on. We need to obviously choose our barrier products and where it sits in relation to the road. But once those decisions have been made, it's about where does it start and stop. Length of need is the term that we use to describe how long a barrier needs to be to shield the hazard that it's intended to protect. So you can see here we've got a length of need, which is measured from this PON, point of need, from that point of need to the start of the hazard. So the point of need is not the very start of the barrier, it's the point at which the barrier becomes effective in redirecting an errant vehicle. So any barrier system at its very start has a section that's not effective in capturing and redirecting an errant vehicle. It will gate. We use that term of gating. So there's several meters in the case of a guard fence terminal. In the case of wire rope terminals, it's the entire terminal. So 10 or 12 meters, something like that. That is not effective. It won't contain and redirect an errant vehicle. If the vehicle strikes that part of the system, it will likely pass through and into the roadside. So the critical point that we need to be aware of with our barrier systems is its point of redirection, its point of need. And that's the point that our length of need is measured from.
And Jamie, for the different products out there, how would you find out the different point of redirection or point of need for those different systems?
The points of need are spelt out in the TCU documents or the product sheets that are available at the RMS website. So it will say something like the point of need is located 3 meters from the anchor point or at post 1 or something like that. It will provide a measurement from the start of the barrier to the point of redirection. And it does vary slightly between different products. So there might be one product that in a constrained situation you would prefer because it has a short gating section. Its point of need is closer to the very start of the barrier than its competitors.
Thanks. And Mark's coming in with a question about the run out line angles and the like, which you're about to cover. So we'll hold that off.
I will. So you'll see here there's a run out line drawn from the edge of the road to meet the hazard. There are some set angles at which we construct that line, and I'll talk to that shortly. So our length of need depends on a few things. The protected width, which you can see here, it's the distance from the edge of the traffic lane to the back of the hazard, the furthest part of the hazard from the road. Our barrier offset affects our length of need, how long our barrier needs to be. If our barrier is quite close to the edge of the road, as per this one, it needs to be quite long. If our barrier was pushed back near to the hazard, we could get away with a relatively short barrier to do the same job. We would end up with a quite wide area of roadside and the potential for rollover within that area potentially. So it's not a treatment that's preferred as a general rule. We're locating our barrier closer to the edge of the road, but looking to provide enough space for a vehicle to pull over in an emergency situation. Our speeds impact our length of need, whether the terminal or the barrier is flared away from the road. If we can flare a barrier to cut off that run out line sooner, we can get away with a shorter barrier length. and our road geometry comes into play. Curved and straight sections are treated differently. So for any given barrier, there are a number of different components that make up its total length. If we have a two-way road, as you can see here, we want to protect that hazard from both directions of travel. So we'll have a length of need determined for traffic travelling from left to right towards the hazard. We refer to that here as our adjacent length of need, the length of need for the traffic lane adjacent to the barrier. And for the opposing direction, we need to go through the same process to work out our length of need. Now that length of need will be the same on each side because we're assuming a fixed angle of departure from the road. So really our barrier will be mirrored either side of the hazard. So our total length of barrier comprises that adjacent length of need, the length of the hazard itself, the opposing length of need, plus these little bits on either end, which are the gating portions of our terminal. So several metres of a guard fence terminal or the entire terminal in the case of wire rope terminals. They're those bits that are ineffective in terms of capturing an errant vehicle. So the question was raised about the run-out line. New South Wales adopts the angle of departure method for determining lengths of need. There are some prescribed angles in Australia's Guide to Road Design Part 6, and you can see them there. There are different angles for different speed environments. They get shallower as speed increases. So we have different columns here for the leading angle and the departure or the trailing angle. So the leading angle is the one that we will typically use. So for our adjacent length of need in a high speed environment, we would adopt a departure angle of 2.9 degrees relative to the edge line for that lane. Now these numbers in degrees are some sort of funny numbers. It's much easier to work with these run-out gradients that are given here. 1 in 20 is the equivalent of 2.9 degrees. So there's a little bit of geometry or trigonometry involved to work out some lengths using these run-out gradients. I mentioned that straight sections of road are treated differently to curved sections. Straight sections are relatively straightforward. We choose our run-out angle based on the speed environment. You can see the angle A given here and here. Despite how this drawing looks, the same angle is to be assumed for both directions. So your length of need will be the same on either side of the hazard. So we construct a line at 2.9 degrees in a high-speed environment and work out how far our barrier needs to extend to cut out that run-out line to shield that hazard. In a one-way scenario, we're only concerned about providing that adjacent length of need, shielding the hazard for one direction of travel. So we can get away with a shorter length of barrier. So again, we have our angle A on the approach side, drawn to the back of the hazard. Our barrier needs to cut off that run-out line. It's typically the case that we would extend our barrier sort of in line with the end of that hazard, so somewhere here. We can shorten things up a bit. No vehicle is going to depart the road at a 90-degree angle, certainly not with any speed, and strike this hazard. So this is where our trailing angles can come into play. So if I take us back to the table, we have a trailing angle of 22 degrees typically that we adopt. And that's the sort of worst case run-out line, the most severe run-out angle that we would expect could happen. So this is our angle B. So a 22-degree run-out line is constructed to the end of the hazard, and as long as our barrier cuts off that run-out line here, we've shielded it effectively. So on the approach side, we have a relatively shallow angle, which is our sort of worst case run-out line and results in a long length in advance of the hazard. And our worst case scenario at the departure end is that severe impact, severe run-out line, and we go with that 22 degrees. That's particularly useful in constrained locations where we might have perhaps we've got a side road or a driveway that sort of curves around in here, and we can't afford to extend this barrier any further. We can sort of work out, all right, we can end our barrier here or locate our point of need here, and we've shielded that hazard sufficiently. Curved sections of road are a little more complicated. We do use the same run-out angles, but we need to construct that line relative to the tangent to the curve at the point that the vehicle departs the road. So this is something that's probably relatively easy to do in CAD if you had this drawn up, but on site in the real world, it's a bit of an iterative thing. You have to sort of assume a location at which the vehicle will depart the road. A less conservative approach is to construct a tangential line between or from the edge line to the back of the curve and assume that a vehicle will continue straight as it enters a curve towards the hazard. So that's a method that's adopted by some jurisdictions, if that makes sense.
Questions coming in. What is typical minimum length of need for a point hazard, small culvert for a one-way road, for example? Now you might not know that off the top of your head, but what things factor into calculating that length?
Sorry, Ken, the minimum length of need for a small hazard like a culvert?
Yes, on a one-way road.
On a one-way road, yeah. So the things that factor into that are how close is the culvert to the edge of the road? And I guess for a start, is the hazard the culvert or the head wall? Or is there a drop-off that you're concerned about as well? So which is the sort of, what are the extents of the hazard that you're looking to shield? And the other thing is, where is the barrier located in relation to the road? So is our barrier 2 metres from the edge line? Is it 4 metres from the edge line? The further away we can push it, the shorter the length you need to provide. So you need to sort of work through the geometry of the situation. Another consideration is the minimum length requirements of the product that you're looking to use. The TCU docs nominate a minimum length for each product, and they really can be quite difficult to achieve, or you might be surprised at how great those minimum lengths are. Perhaps in the order of 60 metres, 80 metres plus terminals. So often a lot more than you might need to provide in order to provide an adequate length of need. Sometimes compromises are made on those minimum lengths depending on your situation, but they are the crash tested lengths, and road authorities are very reluctant to advise anyone to install a barrier at lengths less than those.
So another thing that was briefly touched on was the flaring of the barrier, which would obviously change it. And Mark's asked a question there about the angles then that vehicles might strike the barrier, and whether the performance of that barrier would be altered by the
it's a great question. Flaring is a great tool we can use to better shield hazards, especially where we're constrained and we can't perhaps provide the length that we need to. But wherever we're flaring, we need to be mindful of the flare rate and ensure that it's flared at a fairly shallow rate relative to the line of approaching traffic. If we flare a barrier too much, we're opening up that possibility of a high impact angle and by consequence a high severity of impact. So there are nominated flare rates, and I think I've got some slides on that coming up shortly. But we need to be mindful of those rates, and they're published in the Austroads guide. So when we're talking about flaring, we can flare a terminal of a barrier. So a guard fence terminal can be flared, or the start of the terminal can be offset relative to the line of the rest of the barrier. And we can offset by 600 mil perhaps along the length of that terminal. So 600 mil over 15 meters or something like that. It's a fairly shallow flare rate. That's one way we can achieve a flare of sorts. The other way is to introduce a radius into the barrier, sort of some distance away from the terminal, flare the barrier away for a distance, and then tack on our terminal on the same flare rate. I hope that makes sense, and achieve a greater offset from the edge of the road to the terminal.
Yeah, and I suppose it's just important to clarify there the flaring is a straight line of the barrier of the terminal. You can't bend the terminal, so that's why it's, I suppose, called flaring rather than sort of bending or something like that.
Yeah, any safety barrier terminal must be installed dead straight, wire rope, guard fence terminal. You do see a lot of installations that are curved, especially guard fence terminals. That's a big no-no. We can't be sure that they'll perform as they should. So a flare at a guard fence terminal is achieved by essentially kinking the barrier just before the end of the terminal, or the transition between the terminal and the rest of the barrier, and then installing the terminal on a straight line that flares slightly away from the road. Barrier offset. This is often the first design decision that practitioners sort of like to make. And there are desirable values that we have in mind. It's often the case that we do need to compromise, and we need to be thinking about other elements of design in conjunction with choosing our barrier offset. Our barrier offset really should be chosen to, look, where possible, we should be providing enough space for a vehicle to pull over at the roadside when it needs to do so in an emergency situation. So to do that, 4 meters is desirable. 3 meters is our minimum. It provides just enough space for a vehicle to pull over clear of traffic, but not really to open a door or change a tyre and these type of things. Obviously, lots of times we install barriers at less than 3 meters and as little as 1 meter or even 0.6 of a meter. That's often not the end of the world. It really does depend on your situation. If it's a long length of continuous barrier, an offset, a very small offset is not good because it prevents people from being able to pull over at the roadside when they need to. If it's an isolated short length of barrier on a low volume road and there are opportunities to pull over before and after, then it's not the end of the world. We do need to ensure that we're providing a greater offset at the terminal to avoid nuisance impacts and shyline effects, which I'll go into a bit more. So it really is a case-by-case situation. The closer a barrier is to the edge of the road, the more prone it is to nuisance impacts. A lot of vehicles will depart the road by a small amount. the driver will wake up to what's going on, and they'll recover their vehicle and get back on the road. We don't want those people to unnecessarily strike barriers if we can avoid it. So our choice of offset really is a balance between providing enough space for people to recover their vehicles and enough space to pull over at the edge of the road, but not locating those barriers so far from the road that we're opening up that possibility of rollover and these type of things. The other downside of locating a barrier a long way or too far from the edge of the road is that impact angles are increased. A vehicle will typically depart the road on a bit of an arc, especially if there's a batter that steers them away from the road. So if a barrier is located a long way from the road, we do see some higher severity impacts.
We've got a comment in. I might need a little more elaboration on it from Anand. The barrier offset minimum of 3 meters is not for retrofit type of work / maintenance works. I'm not. Yeah, and it's a question there. I suppose I did want to jump in at this point and sort of mention some of the stereotype cross sections that have been provided by Transport for New South Wales for the rollout in some of the safety programs, which I think are a positive initiative to try to maximise the area of roadside or median that is treated with a barrier system. And I think that the real key with that is to be closely working with your designers and collaborating them with the maintenance teams to understand how they maintain the road, and they will maintain the barriers and the like to, as Jamie said, to then sort of have a strategy of brakes and wider bits to accommodate the activities that need to go on in the road there. And it also is taken into account in where you place brakes in median barriers, if you have incidents and you need to counterflow and operate the road in different scenarios. So it's really not something that you can just say, we're going to go this offset and we're going to do it for 20 kilometres and we're going to brake it only every 2 kilometres or something like that. There's more detail to it, and there's a lot more work in the design required for that. And often you can utilise your different just roadside features, being access points or other features that are in there to give you areas where you can provide these brakes. Yes, because I know barrier offset is a controversial thing. Obviously, the closer you have it to the edge line, the more barrier across the state that will be rolled out, because it's cheaper to do that. But it does come with some operational challenges that need to be sort of factored into things. Now, so we've got some clarification there on that question. I mean, not for replacing a damaged barrier. Okay, so that is, if it's been struck, replacing it, I would assume do like for like. Correct me if I'm wrong, Jamie.
That would typically be the case. Although if you did have a barrier that was repeatedly struck, you might sort of want to dig into it a bit deeper and think if the design or location of the barrier was contributing to that. Yeah.
And the next question is coming from Mitch is around that 3 metre minimum you've got in there, and asking if that's from Austroad's guide and should it be applied to retrofit situations where practical?
Yeah, Austroad's nominates 3 metres as a minimum or desirable minimum offset. I'm not sure, to be honest, the Austroad stance on 4 metres. Certainly the practice in Victoria has evolved in the last few years with a lot of continuous barriers being installed, and a lot initially went in at 3 metres. there was a very strong push to increase that to 4 metres after continuous barriers started being rolled out. So 4 metres is the typical in Victoria for long lengths of continuous barrier. 3 metres is used in constrained situations, and we're talking about roads as well where there's a lot of pre-existing barrier, and a lot of that barrier was in at 3 metres. So look, 4 metres is good, and you'll notice there's a comment up to 6 metres on freeways and highways. That certainly that's a Victorian practice, and the 6 metres recognises that there's often longitudinal services located near the edge of shoulder at around about that 4 metre mark. And if we have the luxury of being able to push the barrier further away, which we sometimes do on our higher class roads, we can go up to 6 metres. We don't want to push beyond 6 because then we're opening up those higher impact angles and rollover possibility. So 4 to 6 metres is the preferred window in Victoria. 3 metres should be considered a minimum in all cases, but for relatively short lengths of barrier, we often do compromise that. And on longer lengths, if we're going below 3, we want to think about doing things like providing refuge bays and ensuring that there are safe places for people to pull over.
In New South Wales, what was I sort of suggest if you're in the development, planning, design phase of a barrier retrofit job or the like, is you get in contact with Centre for Road Safety, make sure you've got the most updated guidance from them on the cross-section stereotypes and desired outcomes. You talk to Jade Hogan's area there, the sort of design area. I think that's what they are in Parramatta there, and just ensure that you've got any other most recent guidance on these sort of offset decision making, and then you get into the specific details of the site and the constraints and taking all of this into consideration. So it's quite a task to design these barriers.
Yeah, another comment from Mitch. He notes that on the New England highway, lots of barriers have gone in at a 1.5 to 2 metre offset. Yeah, and those types of offsets can be problematic. They're sort of, they don't provide space for a vehicle to pull over clear of traffic. If we're sort of looking at 2.5 metres, it can encourage people or make people think that they have enough space to pull over when they don't really. So look, sort of, yeah, there is sort of a window there, 1.5, 2 metres, that does cause some issues.
So Jamie, we might just have a little pause here. We're halfway through today's session, and we'll do as we have done before. I'm just going to put up one quiz question for the group. Remember, you're not being marked on this one. I've made it a little harder this time. It's a little harder, but it's certainly based on your what Jamie's presented in length of need. And I'm also going to give you a couple of minutes to just have a stretch and fill up a coffee or a water or the like. So here we go, launching the poll. Which of these does not influence the length of need of a barrier? Protected width, flaring, post spacing, or barrier offset? So take your, answer that, have a stretch, and fill up a water or a coffee, and we'll be back in 2 minutes from now. Okay. Well, we've had a good response rate there. I'm going to end that and share it with everybody. And well, yeah, almost everybody onto the right answer there. So that's great to see that you've got the concept down pat there. Yeah, the post spacing will impact the deflection of the barrier, but not the length of need of the barrier. And protected width being the width of the hazard you're trying to protect, the amount you flare it, and the offset from edge line will all influence that length of need, as Jamie mentioned. He also mentioned that there are a couple of methods for calculating the length of need, the angle of departure or the run out method, and the angle of departure is the one that New South Wales uses, but just be conscious of that if you're getting designers or you're doing the design yourself, that you're using that New South Wales method. Very good. So that's good, Jamie. They're either all already knew that or they took it on.
Great. I'm realising the time, and I'd better skip through some of this quickly, but bear in mind we will have some time tomorrow to discuss any questions you have, any particular situations that might come to mind. So when it comes to barrier offset, we have these desirable numbers in mind, but there are a few things that we encounter on site that might influence where we do locate that barrier laterally. If there is a curb in play, that limits our options. Our hinge point location, so that's the point at which the start of our batter, the transition between our verge and batter, the width between that hinge point and our edge line is sort of the window within which we must install our barrier, unless we choose to do some earthworks. Table drains and changes in batter slope. Shy line offsets, I've mentioned that term a couple of times. The shy effect is the effect where motorists tend to veer away, to shift their lateral position when they encounter something that's located quite close to their travel path. So something like a barrier terminal that's located near the edge of the road may cause a motorist to shift away from it and potentially encroach the opposing traffic lane. So there are some values given around shy line offsets in the Austroads guide. They differ with speed, and they should really be considered as a minimum offset. If we can't get that sort of offset for the entire length of the barrier, we should at least ensure that our terminal is flared beyond the shy line. And as we discussed earlier, there are some maximum flare rates. We need to be mindful of not flaring barriers by so much that the vehicle can strike them at a too severe an angle. There's that 4 metre desirable offset. It provides enough space for that 2.5 metre wide truck to pull over, clear of traffic. The truckie could open the door if he needed to. So that's good. Here we've got an offset in the order of 2.5 metres, I'd suggest. You can see that this vehicle is probably tracking a bit nearer to the centre line than they otherwise would have if the truck wasn't there. So we do have an increased potential for crashes such as head-ons, of people striking vehicles that are stopped in that emergency lane. It's a bit hard to see what's going on here. We can't tell how long that barrier is. It may be that it's a fairly short length, and someone's just made the unwise decision to stop next to the barrier when they could have stopped at either end of it. But if that is a very long length, we should be providing refuge bays to provide opportunities for people to pull over safely, or desirably, we should be providing at least that 3 metre offset if we have the space available. This barrier has essentially a 0 offset from the edge of traffic lane, or a very small offset of a few hundred mil. It's struck repeatedly. It's a real maintenance burden. Probably the choice of barrier system is wrong here. It's a flexible wire rope, which is great from a safety point of view. From a maintenance point of view, it's a headache. If that was a W-beam system, it wouldn't need to be attended to nearly as frequently as it is. I want to show this slide just to sort of highlight the change in thinking that's happened in recent years. And we're not talking that many years, perhaps 6 or 8. Previously, the preference was to locate barriers as far from the road as possible, or as close to the hazard as possible, subject to the deflection of the barrier. And if you look closely at this drawing, you'll see some barrier offsets. A is our barrier offset of 6.1 metres, 3 metres here, that's pretty standard, 5.5 here. And if you drive along that road, you'll see barriers stepping in and out as you drive along. They're not continuous barriers, they're isolated, they're barriers to shield isolated hazards. But because of the offsets that we're dealing with, there is that increased opportunity for rollover, for higher impact angles with those barriers. So 6 or 8 years after this project happened, another project has come along and decided to install continuous barriers along this section of highway. All of those barriers are at your 3 to 4 metre offsets. So tying in with this old approach has caused some headaches. Embankments, curbs and cuttings, so changes in grade adjacent to the road. You need to be mindful of these when you're locating your barrier. And that's because the trajectory of a vehicle is altered by these features. So here we have the bumper trajectory of a vehicle crossing a curb. And this effect is more severe with the more severe curb type that we have. So a vehicle will typically strike the barrier, it'll ride up and then down again and bounce a couple of times before levelling out. With that in mind, it's desirable to locate our barrier within zones where the bumper height is as close to normal as possible. So our options, or probably our first choice, is to locate it well back from the curb to take that effect out, allow the vehicle to level out. But where we've got curb, we're either in a built-up environment, so we've got nature strips and footpaths and trees and other things, or if we're not in a built-up environment, we're probably in a cut. So we have a cut batter here, and we have a pretty limited verge width to play with. So the far more common scenario is to locate our barrier at the back of curb, or as close to the back of curb as practicable. There may be an option to locate the barrier within some sort of small window where we expect the vehicle to have come back down to around about its normal height. Now, I know in Victoria there's some sort of quite specific guidance around this. There's a little window of a 1.2 to 1.8 metre offset from the back of curb that we use. I'm not sure if that's the case in New South Wales. That's sometimes attractive where we've got underground services close to the back of curb, subsurface drainage, and it's just not possible to locate a barrier here. It's also not a bad idea where we have a limited shoulder width. So perhaps we've got a 2 or 3 metre shoulder and we want to provide a 4 metre shoulder. So we locate our barrier further back from the curb. Similarly with cut batters and fill batters, there are some no-go zones. We don't want to install our barriers in locations where a vehicle is riding up or riding down after striking the invert of a table drain, for instance. Where that's the case, the vehicle is going to impact a barrier at other than its normal height, and there's an increased likelihood of a vehicle penetrating that barrier by either vaulting over it or underrunning.
So Jamie, there's a point that's come in. Currently, with the 1 metre wide centre line, we are adopting on high rank roads, rank 3 and above in New South Wales. We're in a position to afford more than 3 metre barrier offsets.
Yeah, that's interesting. If you can get more than 3, I would strongly support that. 1 metre wide centre lines are great. An even better scenario would be to provide a wide centre line that is wide enough to accommodate a central barrier if you wanted to install one in the future. So, 1.4 at a bare minimum, 2.2 metres within the median, if that was a possibility. It really is a bit of a balancing act. The wider you make your median, the less space you've got for your outer shoulders. But if you can provide greater than a 3 metre offset for your left-hand shoulder, I would encourage that.
Sorry, I think we just got a clarification that that was meant to say not in a position to afford more than a 3 metre offset. So there was a word missing there. Yeah, so that just highlights the challenges I think that you've been talking through.
Yeah, no, and it's the same challenges are presented in Victoria. On some lower class roads, B and C roads in particular, 2-lane, 2-way roads that have some significant volumes, but they're within fairly narrow road reserves. There's lots of vegetation. You can't widen by very much at all. And the result there has generally been to provide a wide centre line of 1 metre, even narrower, and without barriers. And it's often the case that we haven't got 3 metres to our barriers, but where that's the case, we've provided refuge bays at regular intervals.
Yeah. Yep. And I think we'll have a look at a couple of live examples from regional New South Wales tomorrow with some different scenarios, but those are very much the issues that people are dealing with on the ground.
The next consideration in choosing our barrier offset is where is our hinge point? So there's our hinge point there. How close is that to the edge of our traffic lane? And what requirement is there? What width do we need to provide between that hinge point and our barrier to ensure that it has enough sort of lateral support for the system, and desirably to accommodate some or all of the deflection of that system. The desirable situation is that all of the deflection of the barrier occurs within this verge, but in a retrofit that's very rarely achieved. We don't have that luxury. Then we fall back on the minimum widths that are required to support the system, which might be in the order of 0.5 metre. We can get down to even less for the flexible W-beam products. They've been crash tested at less, 2 and 3, 200 mil, 300 mil type thing. For wire ropes, there's a greater requirement, at least 1 metre. So we might have a desirable offset in mind, but our cross-section might not allow it. So we sort of might need to be working back from the hinge point if we don't have the opportunity to widen the formation. I hope you're all seeing this video. I will play it again. It does demonstrate that a barrier located very close to a hinge point or a drop-off, as was the case there, can perform, provided that at least one set, the inner set of wheels of that vehicle, remain on solid ground. So where we are compromising and putting our barrier close to the hinge point, we need to think about how much it will deflect upon impact, and ensure that the vehicle won't entirely pass beyond the hinge point. There are some allowable batter slopes on which we can install a barrier, and the preferred situation is that we don't install a barrier on a slope that's has a gradient greater than 10:1. In a retrofit, we can sort of perhaps get that to 6:1, but desirably we would install a barrier on a 10:1 or flatter slope. And if we haven't got that, we'd undertake some minor earthworks to achieve that. This diagram does show a barrier located at the base of the fill batter down here. I would strike that out. That's not a practice to be encouraged these days. It's not an option. It's not an alternative solution. Guidance in the past has suggested that if you do have those slopes that are considered traversable but are not flat enough to put a barrier on, you can put the barrier beyond the base of that batter, but no, that's not to be encouraged. We want to be putting our barriers at those 3-4 metre offsets from the edge of the road and avoiding this situation.
Jamie, just a quick one that came in back on hinge point. What flexible W-beam products are compliant for installation directly on the hinge point? It comes into play a bit for northern region, it seems, for some of their east-west roads with narrow formations.
Not sure which ones specifically. It's possible that they all are. Where you're locating at the hinge point, you want to be looking to provide longer posts. And I think there's some guidance around that in the product manuals. I'd suggest that you talk to the product suppliers about that. The TCUs nominate the minimum offsets from hinge points, and it's something like 300 millimeters, I believe, for each of them. They're all quite similar. Yeah, I'd encourage you to check with the suppliers if you want to go closer than that.
Yeah, but the key is to get those long posts, isn't it? For yeah, have a chat with the suppliers.
A little video. Come on. This guy hasn't been contained and redirected. It's not obvious why on that first view, but there we have it. That barrier is located just a short distance beyond a drain, the invert of a table drain. The vehicle has gone into the drain. It's hit the bottom of the drain. The bumper has gone down and it's nosed under that barrier. So that just demonstrates the importance of taking these sort of changes in grade out of play, locating your barriers on relatively flat slopes and in front of features such as table drains. So we've discussed barrier offset, the lateral offset of a barrier from the edge of the road. Barrier deflection is the other part of the equation. Generally, there's a fixed distance between our edge line and the hazards that we're looking to shield, unless we're looking to remove trees or undertake earthworks to flatten batters or whatever it might be. We've generally got that fixed width to play with, and some of that width will be allocated to a shoulder in front of the barrier, and the remainder is to allow for a barrier deflection. So these decisions go hand in hand. We might often find that we want to provide a 4 metre barrier offset, but that doesn't afford us enough room for barrier deflection. Or that we might need to change our barrier product, choose one that deflects by less, or modify our product, install additional posts to make it stiffer and deflect by less. So we need to be mindful of the amounts by which our barriers will deflect, deform or deflect when they're struck. Rigid barriers, nothing or next to nothing. Guard fence, so this is G4 or thry beams. in the order of 1 metre is what we typically allow for design purposes. We can stiffen those systems up further by installing additional posts, halving the post spacing, and that will get our deflection down to about 0.5 metre. It does result in a stiffer and less forgiving system, so a less safe outcome. But it is something that's done locally where we might have a hazard that's closer than the rest, and that's what we need to do. The flexible W-beam products, all 3 of them, will deflect by about 1.6 metres under TL3 impact conditions. So that's your pickup truck at 100 k's per hour and 25 degrees. Wire ropes deflect by quite a bit more. 2.2 metres at a minimum. That's one of the TL3 rated products. The Sentry line product is the odd one out when it comes to wire rope. It's a TL4 rated product, which is good and bad. It's available for use in situations where you want to provide that higher level of containment, but it does deflect by more. It's also a higher system and has deeper foundations so that it can accommodate those impacts by the smaller trucks. And it deflects by, something like 3 metres or a bit more. So wire ropes obviously deflect by more than the rest. That deflection can further increase where we've got long lengths of barrier. So the longer a length of wire rope is, the more it will deflect by. And also if the barrier is located on the inside of a curve, on the convex side of a curve, it will deflect by more again. And that's because of that effect where we have a curved barrier in tension, sort of pulling each way, wanting to sort of pull in nearer to the anchor points. Not an issue if the barrier is located on the outside of the curve. In fact, that sort of tension effect will serve to reduce its deflection, if anything. But be mindful where you have long lengths of barrier and or you have a curve in play, your barrier may deflect by more and quite a bit more than the published values. Here's an instance where a wire rope is located very close to that pole. Obviously, it's certainly well within its deflection zone. It does appear that the barrier has been stiffened up with some closer post spacings, but even still, there's every chance that an impacting vehicle would also strike that pole. It's a fairly low speed environment, so the barrier wouldn't deflect by as much as the crash tested situation. I would suggest that a guard fence product would have been a better choice here because our speeds are lower, because we have concerns about deflection. That would have been a better choice. It does often happen that we have objects located within deflection zones. The desirable thing would be to remove or relocate those objects. That's often not feasible. And here's another case where we've got a power pole that's virtually touching that barrier. It's not a by-the-book design. It would be great if we could do better, but in this case, we've gone with a throw beam installation. It is on the inside of a curve, so the risk of someone departing the road there is probably reduced. While this is not ideal, I would suggest that it's better than doing nothing. It does afford some protection to that pole. An effort has been made to stiffen it up. There are also other hazards in advance of this point that are adequately shielded by the barrier. So I guess the moral is, where we don't have adequate space for deflection, think about your choice of barrier product, choose one that deflects by less, and think about measures to reduce its deflection further, particularly reducing post spacings. As I mentioned, minimum length requirements are quite onerous. They can and they can be quite prohibitive for certain products. The wire rope safety barrier minimum lengths have blown out with the MASH accepted products. They might be surprised to see that there's 160 to 180 metres plus terminals, so in the order of 200 metres. Flexible W-beam systems, we're getting close to 100 metres when you include terminals. W-beam, so that relates to G4 and Thri-beam and so on. We can get away with some shorter lengths. And concrete, it's about 60 metres. So be mindful of these lengths and seek to provide them wherever you can. If you can't provide them, I would seek the advice of Jade Hogan's team or equivalent. And it is often the case that we do drop below these minimum lengths. I don't encourage it, but there are situations where we have to, and it's a better outcome to provide a barrier that doesn't meet these than not to provide a barrier at all. I stress that these are based on a specific impact condition, high speed, high impact angle. If you can demonstrate that your location doesn't see speeds that are as high as 100 kilometres per hour, or there's not the opportunity for a high impact angle, it would be reasonable to expect that you could get away with a shorter length and still contain that vehicle. There's a barrier that is way too short. It's a trailing terminal, an approach terminal, and one length of rail in between. So that certainly doesn't meet any of our minimum length requirements. It certainly doesn't provide an adequate length of need to shield this stock underpass, and it's probably a bit hard to appreciate, but there's quite a drop-off in this area here. So the desirable thing here to do would have been to design that barrier to provide a length of need, an appropriate length of need on this side and on this side. Given that we've forgotten about clear zones, we'd provide the same length on this side and a terminal of a type that can withstand an end-on impact. So this is a bare minimum installation. And unfortunately, you do see a lot of this where a token length of barrier is installed. I mentioned run-out areas, and Evan may have as well. Run-out areas, we seek to provide what we call a run-out area behind the terminal of any safety barrier. And it's defined as an area of 18 metres long by 6 metres wide from the point of need of that barrier. And we like to ensure that this area is relatively flat, it's free of any fixed hazards, and that's because vehicles that either just miss the start of the barrier or that strike the barrier end on often end up within this area. It also provides space for the system to operate freely. So it certainly, I encourage you to provide a run-out area wherever you can. This may influence where you choose to start a barrier. If there's an area of roadside available that is flatter and nicer and freer of objects, you may seek to adjust your barrier length to ensure that we provide a good run-out area. So we've designed our barrier. Any longitudinal barrier needs an end treatment, which will have two functions. It needs to provide a crash-worthy end protection for the system. So if a vehicle strikes at end on its speed, it needs to be able to bring that vehicle safely to a stop or not cause it to vault and roll. It also needs to anchor the system to the ground. So especially in the case of The two systems that you can see there, they're tension-based systems. They rely on the system being anchored at either end. They primarily operate by the tension developed within the system, within the rail or the wire rope cables. Now, we're in the space these days where we're dealing with proprietary products. G4 is off the market, so there is a corresponding end treatment for every flexible W-beam product and wire rope product. They go hand in hand. You can't switch things up between different products. So it might be the case that a longitudinal product you prefer for one reason or another. Then you are stuck with the terminal that suits that product, and vice versa. There might be a terminal that you favour for one reason or another. It might be aesthetics, and yes, that sometimes is a deciding factor. It might be the location of its point of need. It might be for maintenance reasons or something or other. If you have a preference for a terminal, that then dictates the type of longitudinal system that you tack onto it. There is a MASH SKT terminal. It's an extruding type end terminal. On the right, you can see one in action. The rail has extruded out the side into an area here. So that's another reason to provide a run-out area, an area clear of any fixed objects, especially where we have extruder type terminals. Barrier transitions. Now, I'll point out that this vehicle is facing the wrong way. This is a one-way carriageway where the direction of travel is towards us. This transition is not ideal. The point of need for this wire rope system is back here somewhere, and the point of need for this guard fence with a breakaway terminal is here. So there's a length of roadside between here that's not effectively shielded. There is a possibility that an errant vehicle will pass through that gap. The desirable thing would be to overlap those points of need so that there's no opportunity for that to happen. In this case, the points of need are overlapped. The distance between the two systems is questionable. The desirable thing to do is to provide for the width between the systems to be at least as much as the dynamic deflection of this upstream system. So in the case of a wire rope, we're talking 2 meters or thereabouts minimum. Another common type of transition occurs at structures where we have a rigid system transitioning to a semi-rigid system, an off-structure barrier, and then perhaps overlapping again to a wire rope. This drawing comes from the RMS suite of standard drawings, and it provides a typical detail for transitioning between a W-beam and a rigid barrier, and a gradual increase of stiffness is provided by transitioning to a thri-beam in between. So wherever we're directly transitioning from one system to another, we need to be mindful of the potential for a vehicle to pocket. If we have a more flexible system transitioning into a rigid system, if they impact the semi-rigid system, they might then snag against a point here where the system becomes rigid. So at structures, we do that by transitioning over a short length to a thri-beam system, which has an in-between rigidity. So a few parting tips on designs, and I'm happy to answer any questions tomorrow. We'll have more time then on any specific situations. But I really encourage you to understand the different products that are available. And it is a changing landscape. There's a whole new suite of guard fence terminals of wire rope products. Know the differences between those systems to inform your choices. Minimum lengths of barrier are really, as we've seen, they're really quite large. So be mindful of those when you're designing and installing barriers. The length that you have available might influence your choice of barrier system. Avoid short breaks in barrier where possible. Short breaks leads to more terminals. So it can be the case that providing a succession of short barriers instead of one long barrier is actually a more expensive outcome. Terminals are also the most hazardous part of the system. So if we've got lots of exposed terminals, that has a lesser safety outcome than one long continuous barrier. Now the terminals are crash tested, and if they're installed and maintained correctly, will provide safe outcomes, but there still is some potential for things to go wrong. So I'd encourage you to avoid that. Encourage you to flare barriers wherever you can. I think this is an underutilised thing. Do be mindful of those maximum flare rates. Flaring is especially useful in constrained locations where you might not be able to achieve the length of need that you would like. It's a great thing to do in your driveways and side roads. You can get those barriers outside your vehicle swept paths. You can open up sight lines better for people entering from the side roads. Think about providing run out areas wherever you can. And think about all of those things at the roadside that the barrier needs to integrate with. I can't stress enough how important an initial site visit is when you're thinking about a barrier treatment. Get out there, take all the photos you can, do a dial before you dig, understand what you need to work with and around out on site. There are things that might need to be relocated, reinstated, that will influence the location of your barrier and how you go about designing it.
Absolutely, Jamie. And when we get around New South Wales and come to your regional offices and do the sort of second part of this training course where we provide you some sites that we've identified and you go out to do barrier design on them, everybody finds it a very interesting experience to take the theory and the principles and then try to apply it in the real world where you have all sorts of challenges that pop up. So getting out on site is absolutely critical to barrier design. And Jamie, just while I get some slides up, do you want to just answer this last question? If you do not have any space for a run out area, what would be the alternate approach to mitigate the issue?
Yeah, and look, this does happen. If your roadside is consistent in terms of batter slopes and frequency of hazards, then there's probably no preferable location to terminate your barrier and provide a run out area. Look, certainly in new roadworks projects, it's nice to construct a run out area, a relatively flat pad. In retrofit situations, that's not a done thing. And really locate your barrier terminal sort of in the best possible location that you can within the roadside that you're working with.
And I think, as you mentioned at the end there, flaring could assist, am I right? A little bit? Yeah, maybe not.
Look, if you've got, and it is often the case in constrained locations, you've got trees and poles and things near driveways, and you just can't provide a run out area. You want to shield those things as best you can, and flaring helps.
Yeah. All right, thanks, Jamie. And yeah, as Jamie mentioned, if you think of any questions in the follow-up from all of that that you want Jamie to cover off, we've got some time allocated tomorrow to just do any Q&A. But I wanted to finish off today just touching on motorcyclist considerations, and it's something that pops up quite a bit with road safety barriers. And as I just want to briefly, I suppose, dispel a few myths out there, and also give you some ideas on what you can do if motorcyclists are a particular concern in areas. But the first thing I just wanted to cover off is some research that's been bubbling away, actually out of New South Wales, that has been, for the last 10 years or so, looking at motorcyclists striking barrier systems. It all sort of came about because of the uproar from the motorcycle community around the mass rollout of wire rope safety barriers and their concerns around those. And so there was some funds invested from the different jurisdictions to University of New South Wales to start to do the analysis of this. And really these two gentlemen have been leading a lot of that research, and there's quite a number of reports available from Van Batchen and Gabrietta. And I think this first one, I mean, it's a very overview sort of thing. But we see here that in the crashes in this particular study over a period of time, where we see there that the total crashes here in fatalities, and then we see, this is for motorcycle crashes, and we see barrier crashes only representing a tiny proportion of those. There's quite an unknown there, and that's predominantly due to police reporting and unknown what the fatal blow was caused by, and particularly in New South Wales. So that might be a reporting thing that you need to look at, or how they've done the research. But nonetheless, barrier strikes are quite rare in terms of the fatal and serious injury for motorcyclists, but they do exist. And when they come into play, so when motorcyclists strike barrier systems, what are the barrier systems that are being struck? Well, guardrail products are the dominant, absolute dominant in terms of fatal and serious injuries involving motorcyclists striking them. They're a small percentage of the trauma for motorcyclists, but when you get into that small percentage, it's dominant that it's guardrail. In fact, I'll give a prize out to the person who can quickly write in the dominant reason why they think guardrail pops out as the number one for motorcyclist trauma striking barrier systems as the barrier type. So first one to pop that into the Q&A can have a prize. So you can see there that there's some different things that are being struck, and concrete next, wire rope very, very small, and then so I'm going to give it to Stefan, because most used system is pretty much it. And a few others got in there with that as well. So Stefan, you're on to your second prize for this course. I'll just jot that down. Yeah, so there's just a lot more of it out there. The other slight thing is that we don't tend to use other products on popular motorcycle touring routes. That's because of a couple of reasons. One being the radius of curves. So if you've got a popular motorcycle touring route, it's usually quite windy, hilly, scenic and the like. And you cannot install a wire rope system, because you'll remember that one of the requirements is that minimum 200 meter radius of the system, because it's in tension. It'll pop into the middle of the road if you tension it up, and it's on a sharp curve. So on those routes, it's always going to be guardrail. It's the most out there, and there's the minimum length requirements, which Jamie touched on, and wire rope's very significant there. So it's really used on those long, straight-ish roads where fatigue is the issue and people are leaving the road, falling asleep and the like, and motorcyclists aren't tending to do that as well. So quite a number of things in there. But the addition of barrier protection devices and motorcycle retrofits to barriers has been very successful in targeted programs. So a 74% reduction in fatal or serious injury, that should be FSI, for barrier protection treatments in a dedicated program, and some sort of targeted routes being treated has had some significant reductions. And that's sort of the way I think that is appropriate for thinking about motorcycle and barrier systems. It's about knowing your popular motorcycle routes, where the motorcycle risk is highest, and then retrofitting those with appropriate features. Up the sort of Pacific Highway or something like that, retrofitting the whole lot of it with motorcycle barrier protection devices, I think, is not the best use of your limited road safety funds, because we know that crashes of motorcyclists with barriers in those sorts of scenarios is extremely rare. And we would be better investing those funds in other environments. Just a bit of the mechanics of it. The motorcyclists striking barriers have forces that exceed thresholds of being killed in this sense in a number of areas, but thorax being the major contributor. And to boil down sort of the 10 years of research that they've been doing into a couple of quick things, half the motorcyclists are off their bike and sliding when they hit the barrier system. The other half are upright and trying to stay on the bike, and they hit the barrier system and they go over the top. Motorcyclists are not sliding along the system the way it's been designed. So a couple of videos of that for you. I'm just going to mute these. So that's motorcyclists trying to stay on the bike and going over the barrier system. Here's a crash test dummy. You see the rider goes over the top very quickly. Hope these are streaming for you. The bike's actually doing exactly what we want out of a barrier system, just sliding along it, but we just lost over the top what we're trying to protect. And the other is where the rider is off the bike and sliding and strikes the base of the barrier system. And that's about half the time that they're already off and sliding and hits a post. Here's another motorcycle dummy in a crash test scenario, sliding along somewhere near the bike, but they will pretty much always separate, and the rider pretty much always finds a post and strikes the post. And you see there the post, even though that's a flexible system, the post pretty much doesn't budge with the weight of a motorcyclist. So, having that all in mind, what can we do? No prizes here. We've already talked about it, but some sort of underrun protection gets different names. Rub rail is sort of the public domain name for that system that goes under and under sort of G4 systems. But each flexible WB product has their own motorcycle underrun protection proprietary device. And the suppliers will gleefully tell you all about them if you ask. So if you're sliding along as a motorcyclist at 80 kilometers, 70 kilometers an hour or something, you would not want to be hitting one of those posts. If it was retrofitted, it would be better to hit that and slide along it and dissipate your energy. And these have been tested and shown to be fairly effective. I'll show you shortly what the tests are. So these can be retrofitted to existing G4 systems, and you use a little bracket in there to stick it out in line with the system. You'll notice here that the end terminal does not have this attached to it, and that is because nobody's tested that. Nobody knows what it would do to the functioning of the end terminal. So if you see people fitting underrun protection to end terminals in the traditional sense, you want to stop that happening. Now, that being said, there are products out there that have been trialled. They're not approved for use in New South Wales, but potentially something to be trialled on some popular motorcycle routes of products that they're not connected to the terminal itself, but they sit out. So if you have an interest in that, you can get in contact and I can provide you all the details of those products and the suppliers. But they are accepted for trial in Victoria and South Australia. Use them as well. And you can see them there added to a terminal, which looks like it has a little bend in it, which I'm not too happy with. But anyway. I won't spend long on this, but basically there's a particular dummy that is used for motorcycle crash testing. It's been slightly modified from an existing dummy. The dummies are very unhappy with the fact that they've been chosen to be motorcycle dummies because the impacts are severe, as you would imagine. So here's some Transport for New South Wales test footage. There's a dummy sliding at a post at 60 kilometers per hour, direct hit, and you can see it pretty much obliterates the dummy and is easily enough force to kill the motorcyclist. So this is pretty much the European test protocol, which is done. But you can see then that the addition of underrun protection sort of directs the energy along the system. And the test is one shot directly at the post, one shot between the post, and checking the forces impacted on the motorcyclist. And they perform quite well under those tests, but as I said, they're a 60 kilometre per hour test, and you just got to take that into account. There's a few other sort of products out there that aren't yet accepted for use in New South Wales, but I encourage you to have these discussions if you have these particular scenarios and potentially get them as something that could be trialled. And again, you'd be talking to the likes of Kate Hogan and her area to discuss these and potentially others at Centre for Road Safety. But you have post capping available to try to lessen the impact of the motorcyclist that goes over the top. Wire rope systems, well, we saw there earlier that motorcyclists striking barriers are a very small, a small percentage of motorcycle trauma. And then within that small percentage, an absolutely tiny percentage involves hitting a wire rope system. So we're at a very, very small percentage of trauma out there. But the motorcycle community has this in their mind as the biggest issue. I'm a licensed motorcycle rider. I'm not an active motorcycle rider, but I have spent many, many years with the motorcycling community, working on road safety infrastructure. And a lot of them are skilled up and trained up enough to know that this is not the big issue that they should be lobbying and challenging for, that there are far bigger things that they can be doing and lobbying for that will improve motorcycle safety, but it still raises its head. So for me, if it's a popular motorcycle route, my choice of barrier system isn't going to be a wire rope system anyway. And the reason for that is it's probably likely got some curves, so I can't use it. I don't have the ability to add an underrun protection device that is really good and tested. So I'm going to use a flexible W-beam system and its proprietary underrun protection. That's just going to be the choice of barrier system. But for these long, Hume Freeway upgrade or whatever it is, I'm still going to use wire rope safety barrier because the motorcycle risk is so minuscule. It's negligible in terms of strikes with the barrier. These are just some research that shows actually installation of barrier systems is a significant improvement in motorcycle safety all round for a whole lot of other reasons. I'm going to jump past that. But really, wire rope systems don't have anything that we can retrofit that meaningfully are tested and proven to improve motorcycle safety. We do have a device that is used around the country, not approved for use in New South Wales at the moment. Maybe, well, there's a suite of products, but they're post cushions. So they're basically football goalpost padding, the equivalent of that for the motorcyclist that's going to hit it. So, of course, that is not going to be as effective of a redirecting device where you would run along the system. This is trying to absorb energy over a very short, it's padding. Never been tested under the European test protocol, and I suspect that's because the suppliers know that it's not going to pass. So I have used these in the past and really predominantly as a PR device in the sense that we know it's going to do something in some scenario, but as an investment in road safety, it's really not great. But if it means I can get these barrier systems in the way we want, then it's something I might do. So maybe if you're doing a big route and you've got one particular spot where you're concerned about motorcycle safety, or the community, the motorcycle community is jumping up and down about it, you could retrofit some of these just to sort of alleviate. Really though, if you agree that it's a motorcycle risk at that location, switching your barrier system to something you can fit an underarm protection as you go. Here we did use it on the South Gippsland Highway, which is the route down to the Motorcycle Grand Prix, with a central barrier system. This was about 10 years ago though, and this was before we had back-to-back flexible W-beam systems that we could use. So wire rope was going to give us the best safety outcome for passenger vehicles by a long shot compared to type B, or in your case G4 systems. So we really wanted to push to get the wire rope system. The motorcycle community was angry because there's a lot of motorcyclists, so we retrofitted with these devices. But each one of these things cost us $44 per post addition, and when you do it for 5 kilometers of this, it racks up. So if I was doing this these days, back-to-back W-beam, flexible W-beam system with underarm protection every time. I'm going to jump through that. Lots of other products out there that pop up in the motorcycle safe, fabrics that stretch over. Really just you have to go to RMS website and check out what's approved. And if it's not, and you still want to try and trial it or something like that, you need to talk to the Jade Hogan's area. Flexible delineators on barriers is standard, so that's nothing new there. And just be careful about any retrofit installations that they're done right. People like to attach them to the post, and that's not correct, because you can get an arm and a leg through there easily, and that'll happen. Check the product descriptions. Any gaps or anything that you can run into, obviously things that you want to rectify. So products accepted for use in New South Wales: Biker Shield on Ram Shield, Hyasa Rail, MPR on EasyGuard Smart or G4. Legacy products, the public domain rub rail system. So you wouldn't even use that on existing G4. You would use one of the proprietary products that has been tested. And not approved products, but as I say, you might consider trialing these at some point. The polybuffer system on end terminals, the post capping, maybe the fabric system, stack cushions in those very isolated scenarios, and individual post protectors for motorcycle safety, biker mate, impact protect. But as I say, I'm happy to chat to anybody if they've got an interest. We've just ticked over time, so I think I'm going to call it quits there and pick up any questions that came back on that next time. So you do have a quiz at the end of this. If you haven't done your assignment, please do it. And we'll see you tomorrow morning at just a little bit before 9 o'clock for a chance to win a prize. And there was a question in there that I will answer first thing tomorrow. Thanks, everybody, and have a wonderful day.